we're going to look at the quantum model of the atom. Okay, and the quantum model of the atom looks like this cloud, basically. Okay, and the quantum model gives us basically a region to look for an electron, right? We've identified where electrons sit in their orbitals, right? Our orbitals are electron pockets. So we've identified where these electrons sit, but the quantum model kind of tells us the probability of finding an electron in an atom. Okay, and so it tells us that the probability of finding an electron increases as you get toward the nucleus, right? Because there's more shells closer to the nucleus, which means electrons are closest to the nucleus. Then we add a shell, and as we move outward, electrons have more space to roam, and then they are bouncing around more and more and more. So the probability of finding an electron increases as you get closer to the nucleus. Okay, that's where the cloud of electrons is more dense. Okay, you're more likely to find an electron in here than you are as you move outward. Okay? That just has to do with atoms being in generally a circular shape, right? And so as you're closer to the nucleus, they have less and less space to move. As you move outward from the nucleus, they increase their ability or their space they have available to them to move. Do you remember the proportion I gave you for the atom? Right? If the nucleus is the size of a marble, what's the size of the rest of the atom? A football field, right? So the nucleus is the size of a tiny little marble. The whole atom is the size of the football field. So electrons have more and more space as you move outward for them to roam. Okay? So the quantum model looks like that. You might want to sketch down what that quantum model looks like. It's just basically a cloud, right? That's darker in the middle. It's more dense. Probability of finding an electron in the middle of that cloud near the nucleus. And then as you move outward, you lose a little bit of that likelihood. Okay, so the quantum model and the electron orbitals that we looked at last class go hand in hand. So today we're going to talk about something called the quantum number, an electron's quantum number. And every single electron within an atom has its own specific quantum number. And the quantum number for an electron is kind of like its address, right? Where can it be located? Okay? So the quantum number, it tells us specifics, or it specifies the properties of the orbitals and the properties of the electrons within the orbital. So every single electron within an atom has its own specific quantum number. And I want you to think about it like the address of that electron. Okay, and we're going to determine what the address is for that electron. Every electron has a specific quantum number that gives us the best probability of locating that particular electron. Your address has how many parts to it? Right? It has the house number, the street, the city, and the zip code. Right? You have 4 parts to your address. Every quantum number has 4 parts to it also. Okay? 4 parts. And so I'm going to briefly list the 4 parts here, and then we're going to break each of them down into much more detail. So if you want to just listen for these first 4 parts, that's fine. But I'm gonna list each 4, and then we're gonna break them down further and further. Okay. So the first part of our atom, our quantum number, tells us the energy level of that electron. Right. Each individual electron has a quantum number. And the first part of our quantum number, okay, and I'll show you. Quantum numbers are usually listed like this: N, L, N. That's right. There's 4 parts, and they're listed with commas in between. You don't have to write that part down yet. But when I say first part of our quantum number, right, I'm talking about this guy right here. Okay, there's 4 parts, and they're listed with commas in between. I'll tell you what each of those things mean here in just a little bit. But there's 4 parts to the quantum number, just like there's 4 parts to your address. the first part tells us the main energy level. So basically, what shell is it in? How far is it from the nucleus? Okay. Second tells us the shape of the orbital that it's in. Can someone tell me some of the shapes of our orbitals? Right, there's 4 of them. Yes, sphere. Okay, and the letter name for them. S, P, D, and F. So there's 4 possibilities for the second part of our quantum number, right? It can only be in one of those 4 shapes, S, P, D, or F. The third part of our quantum number tells us the orientation of the orbital. All right, an orientation tells us where is it located around the nucleus. Okay, where is it located around the nucleus? If you think back to when we talked about our p orbitals, we said there's 3 versions of the p orbitals, right? One of them's on the x-axis, one of them's on the y-axis, one of them's on the z-axis, right? Do you remember talking about that? When they looked like they were just at kind of a different angle. That's what orientation means. Which version of the p orbital is it in? Or which version of the d orbital is it in? Okay, there's only one version of the s orbital, right? It's a circle. It's a sphere. Only one version of that. But the p and the d and the f orbitals have multiple versions, right? Or multiple orientations they take around the nucleus. So that's what the third part of our quantum number means. The last part of it's really easy, and it's just the spin state of our electron. And if you think back to last class when we did our orbital diagrams and we drew the little arrows up and down, right? Those were telling us the spin states of our electrons. And so there's either a positive spin state or a negative spin state. So only 2 options for the last part of our quantum number, right, which make it a little easier. So now that you know what each of them kind of mean, now we're going to break each part of the quantum number down more specifically. Okay, so we're going to look at the first part of our quantum number, which is the principal energy level. Okay, and it's called the principal quantum number. It's symbolized by an N, a lowercase n. Number tells us the energy level of our electron. The energy level of our electron. So when we talk about energy level, we are essentially talking about what row is it in on the periodic table, right? Essentially. There's some exceptions, right? Like the 3D orbitals are really shifted up a row. The 4F, they're shifted up too. Okay, but the way you find out an element's or an electron's principal energy level is from its electron configuration. Okay, so let's say we are looking at the very last electron that gets put in for sulfur. Okay, I want you to think about just the very last part of sulfur's electron configuration. The very last part of electron configuration for sulfur is 3, what? 3p4, right? Sulfur's 1, 2, 3, 4. Does that make sense, right? There's a lot that goes before that in its electron configuration, but 3p4 is how sulfur ends. Do you agree with that? So the main energy level, or N, is this, right there. That coefficient that comes in front, N is equal to 3. It's on the third energy level, right? It's the third shell out from the nucleus. Okay? That's where that N number comes from. So again, it corresponds kind of with the row on the periodic table with the exception of the d orbitals or whatever. But you follow exactly what it looks like in its electron configuration. Okay? So that's where that 3 comes from. Okay, so let's try another one. What would N equal for the element copper? N would equal what? N would equal 3 or 4? 3. N equals 3 because although it's in the 4th row, this is tricky, right? Although it's in the 4th row, it's in the 3D orbitals. 3D orbitals. So you can't just pay attention to what's happening on the periodic table. You have to think about its energy level. So it's in the 3D orbitals, so N equals 3. Okay, does that part make sense? What would N equal for calcium? What would N equal for calcium? Hold up a number. Let me see a number. 3, 4, 2, 1. What do you think? Good. N equals 4. Because calcium is a 4s2. Oops. So that energy level is 4. Okay, so that would be the first part of our quantum number, right? If we were listing the quantum number for the last electron in calcium, we would say 4, comma, and then we'd have 3 other things that go along there. Okay, that's the first part of our quantum number. Easy enough? Okay. Values of n can only be positive integers 1 through what? 1 through what? What's the highest energy level we could have? 7. Yeah, 1 through 7. When we're doing elements only, which is all that we will do. We're not going to do quantum numbers for, anything else. 1 through 7. Positive integers 1 through 7. You don't have an energy level of 0, because there's no 0. That's just not a thing. Okay? So 1 through 7. Okay, I don't need that part. Okay. Values of n can only be positive integers 1 through 7. All right, the second quantum number is called the angular momentum quantum number, which sounds a lot more intense than it really is. Okay, this one is symbolized by an L. Okay, and I always write my L in cursive because if not, it looks like a 1. Okay, so L is our second part of our quantum number, right? It goes N, then L, then 2 other things we haven't talked about yet. Okay, L is our angular momentum quantum number. Does anyone remember what the second part of our quantum number tells us? Right, do you remember? First part tells us energy level. Second part tells us the shape of the orbital. Okay, and there's 4 options here, S, P, D, and F. Unfortunately, L just can't be S or P or D or F because it's a quantum number, not a quantum letter. Okay, so we give each of these letter shapes of our orbitals a number that corresponds to it. Okay, and so it looks something like this. Okay, if it is an S orbital, if that electron is found in an S orbital, then L equals 0. If it's found in a p orbital, then L equals 1. Okay, and so on and so on. Okay, so that little chart you need to have down in your notes somewhere. Values of L can be 0, right? That would indicate that it's an S orbital through n minus 1. Okay, and there's some kind of exceptions to that rule, but that's the general formula, and I'm going to show you why that is the case. Okay, 0 through n minus 1, and like I said, there's some limitations to that if n gets too high, but I'm going to write all these out just so you can see what I'm talking about, but you don't have to write this whole thing, okay? So if n equals 1, that means we are on the first energy level. We're in the closest shell. And what's the only possible orbital type we can have on the first energy level? S. The only possible type we can have for the first energy level is an S orbital. So if n equals 1, L can only equal 0, right? Which also happens to be n minus 1. Okay? 1 minus 1 is 0. Okay? If n equals 2, what are the only possible shapes of orbitals we can have for the second energy level? 2s and 2p, right? Are there 2 d orbitals? No. Are there 2 f orbitals? No, right? So if we have 2s, that means it's a 0. And if we have 2p, it could be a 1, right? So L values could be 0 or 1, depending on what electron we're looking at. Okay? Are we seeing a pattern there? If n equals 2? So if n equals 3, what are the shapes of the orbitals that we could have for the third energy level? Okay, think about our third energy level. We can have s orbitals, and we can have p orbitals, and we can have d orbitals. So s corresponds to a 0, p corresponds to a 1, and d corresponds to a 2. Do we see what pattern is happening? Okay, the last one I'm going to show you is that if n equals 4, then L could equal S, P, D, and F orbitals, right? We could have any of those versions, right? The quantum number could be 2, 0, then something, something, or it can be 2, 1, something, something, right? It's not like all of these L values would go into the quantum number. It depends on where the electron is located, okay? But those are the possibilities for L. So the basic formula for L is 0 through n minus 1, okay? If we get up to n equals 5, what are the possibilities for L? What types of orbitals can we have on the 5th energy level? S, P, D, and F, right? There's no orbital that's past that. So that's where the rule kind of stops working, right? You can't have an L value equal to 4 or above. It won't work like that, but it's easiest to just see it when you are corresponding with the shape. So I'm just telling you, those are the main kind of formula for finding L, but there's lots of possibilities for that. Okay, here we go. Okay, we just talked about that, blah, blah, blah. Okay. Third part of our quantum number is called the magnetic quantum number. And we symbolize this just by an M. Okay, some people call it MS, I think. I just put it with an M, okay? And this tells us the orientation of our electron around the nucleus, right? What version are we looking at? All right, so we're going to look at finding M based on this rule of values being negative L to positive L. And we're going to look at sulfur. Okay, so sulfur ends its electron configuration in 3p4. Do you agree with that part? 3p4. Right? And we are looking at the electron address or the quantum number for the last electron placed in sulfur. That's really important. The last electron that gets placed in sulfur. And so to be able to visualize that electron, we're going to draw out the orbital notation of 3p4. Okay, orbital notation is when we have the arrows, right? So the 3 P's look like this. 1, 2, 3, right? 3p. Why does it have to have 3 lines? Right? There's 3 versions of the p orbitals. Each can hold 2, right? It can hold 6 total electrons. So 3p4. Remember, there would be, if we were wanting the whole orbital notation for sulfur, there'd be a whole bunch of stuff before that, right? But we're just concerned with the last electron that gets added. So when I add my 4 electrons here, do I go 1, 2, 3, 4? No, right? I have to go all the way across, then back. And in this case, it's really important that we add the positive first, and then we go back and add the negatives, right? Before I said it doesn't really make a difference. Here it does, okay? So we're going to add 1, 2, 3, and 4. So the last electron that I added was this one. So this is the electron that we are concerned with. Okay, that's the electron we're trying to find the quantum number for. That's what we're trying to find the address for, blah, blah, blah. Okay? So we said that M values range from negative L to positive L. So let's first find out what N and L are. Let's start writing the quantum number for sulfur. Okay? What's the energy level, or the first part of our quantum number? 3, right? First part of our quantum number is 3 because our energy level is 3, right? That's where that comes from. The p orbital tells us it's what number goes with the p orbital shape? 1, right? It goes S, P, D, F. So it's a 1. That means it's a p orbital. Now it says our M values can range from negative L to positive L, which means in this case it could be negative 1, 0, or 1 for L. Okay, and these numbers fit right here. Negative 1, 0, 1. Okay, so based on which orbital it's in, the electron that we're looking at is in that orbital. That's our M value. Okay, that's it. It will always correspond. Those M values will always correspond to the number of orbitals you have in that shape. Okay? They will always, always, always correspond that way. Okay? And then I'm going to show you the last quantum number here really quickly because it's the easiest one. The last quantum number has to do with the spin state of the electron. And the only options are positive or negative. So this electron that we're looking at, is it spinning in the positive direction or the negative direction? The negative, because it's pointing downward. right? That's the only indication. It's pointing downward, so it's spinning in the negative direction. So the very last part of our quantum number is negative 1/2. I don't know where the 1/2 comes from, but it's a negative 1/2 or a positive 1/2. That's the only two options for the last part of our quantum number. Negative 1/2, positive 1/2, right? Positive 1/2 would be if it's spinning upward. Negative 1/2 is if it's spinning downward. So this right here is the quantum number for this electron, right? That's the address. Third energy level, p orbital. It's in the first version of that orbital, right? And it's the one that's placed second. Okay, it's the negative spin electron. Okay, how do we feel about that? Okay, so far? I want to show you this M number on our d orbitals now. Okay, so I want to show you one on the d orbitals. So let's say we're looking at titanium. Let's do titanium. So we're going to go ahead and just basically find the quantum numbers for the last electron placed in titanium. Okay. And so titanium is in what orbital? It's a transition metal. It's Ti. It's in the 3d orbitals. Agree? We see it? It's 3d what? 3d2. Okay, so you can write it out here if you want. You don't have to, but you can. And then I like to draw the orbital notation, the last part of it, because it helps me see what version of my orbital is it on. Okay, so 3d gets how many lines? 1, 2, 3, 4, 5. Right? Because the d orbitals can hold 10 electrons. Each orbital can hold 2. Okay? So before we label anything else, let's go ahead and start with our quantum number for titanium. It's in the third energy level, which means the first part of our quantum number is a 3. Right? Okay, that's where that comes from. First part of our quantum number is a 3. Second part of our quantum number tells the shape of the orbital. And what shape is it? It's a d orbital, which corresponds with what number? S, P, D. So 2. Okay, and that's from that little table that you put in your notes, that little table, okay? S, P, D, F. Okay, so right now we're saying third energy level, D-shaped orbital. We can't go any further until we go back to our orbital notation, okay? So titanium only has 2 electrons in the d orbitals, which means I enter them 1, 2. Right? Are we agreeing with that? So the electron we are concerned with is this one, and I think it's helpful if you circle it. So you're really focused in on just that electron. Now to find out what orientation it has or what version of the d orbital is it in, we say M can equal negative L to positive L. Okay, so L equals 2. So I say negative 2, negative 1, 0, 1, and 2. Okay, do we see how those numbers fit all the way across? Negative L to positive L. Okay, negative L to positive L. Okay, so that means the third part of our quantum number is a what? A negative 1. Good. Okay, and the very last part of our quantum number is the easiest. It's the spin state, so what should it be? Positive 1/2. Plus 1/2. Because this electron's spinning upward, right? It's pointing upward, so it's a positive 1/2. So the only 2 options for our last quantum number are positive 1/2 or negative 1/2. Okay, so I have that here. Only has 2 possible values for the last one. It's called the spin quantum number. It is only positive 1/2 or negative 1/2. Only 2 options. Okay. Whoa. A little bit away from me there. Okay, raise your hand if you think you have an idea or you have a guess of what it is. Okay, I'll give you about another minute. People are still working. It's sodium. And we know it's 3 and then what? S. We know it's 3s. So if I draw out the orbital for 3s, right, there's only one version of a 3s orbital, which means it gets a 0. Okay, there's only one version. And since we know it's positive 1/2, that means we're looking at the first electron that gets put in. Okay, so if there's only one electron there, that means we're looking at 3s1, which is sodium. So you were really, really, really close. Okay, let's try another one. Find the element if it is you might have to draw it out to help you see how many electrons and all that kind of stuff. You might have to draw out the last orbital. Okay, we know it's got to be in the 4d orbitals. Can anyone tell me, take a guess on what element it is first? Lizette, what do you think? Silver. I would agree. So this is how we know that. We know it's in the 4d orbitals. Is everyone on the same page with that so far? 4d orbitals. We know it's got to be on this orbital, and we know it's the negative spin state. So it's the second electron that gets put on that fourth orbital. It's the second electron that gets put on that orbital. That means we have to go 1, 2, 3, 4, 5, 6, 7, 8, 9. And we're looking at that electron, right? Remember, we still have to follow the rules of filling all the way across and then coming back. So if we're looking at this electron in particular, that means that's electron number 9. So 4d9 would mean that we are looking at silver. Okay.